Yep. Forces. Let's talk motion a little bit. Okay, so we've been talking, so let's close up those, please. We've been talking about studying motion, right? Studying kinematics is the study of motion, right? It's our way of very precisely describing motion of an object, okay, with time. We'll get more involved with that later, okay? But we have a pretty good grasp of that. I think the hardest stuff we do is pretty much already done. Things don't get any harder mathematically than just doing the trig associated with adding up vectors. We're going to, in a while, well, we're going to do some more vector stuff. And then eventually we can get to some more elegant ways to solve certain problems by avoiding vectors completely. Just like in calculus, like we try to avoid using the difficult derivative rules when possible, right? So for example, those of you in calculus, we talk about wanting to avoid using the quotient rule whenever possible because it's a mess, right? So if we can pre-write a problem in order to avoid the quotient rule, we do. In physics, and something that's analogous to that is we would like to avoid using vectors whenever possible because vector math is harder than scalar math, right? Scalar math is just adding and subtracting and multiplying, but vectors get harder, right? So eventually we'll come full circle on this thing, and we'll find in some cases some ways where we can very elegantly, if we're really careful about it, we can avoid the vectors. Okay, so we've talked about the study of motion, but now we're going to start to talk about the cause of motion, causes of motion. So what do you know about that?
Forces.
Okay, forces are definitely going to be involved, right? If there were no forces in the universe, it'd be a pretty boring place. If there were no forces, well, things wouldn't even exist. But I mean, even if we just eliminated something like just the electromagnetic force, so we couldn't push on things and pull on things, it'd be pretty boring. Stuff would just sit there, right? So if we want to get from how do we describe motion to how do we study the cause of motion and predict what motion is going to occur from interactions, we got to talk about forces. Okay, so let's start at the start here. What do you know about forces? Tell me what you know. What is a force? Okay, they have a direction. Very good. Forces, so what's that probably tell us? What kind of quantities are they? Vectors, okay. Is that what you're going to say, Stan?
I was going to say force is mass times acceleration.
Okay, well we're not going to quite get there yet. Right now we're going to be qualitative about it. We're just going to talk about forces in terms of, and I think that's a good way to do it in physics, is to try to build it up from a qualitative standpoint to a quantitative standpoint. But there's some benefit to just understanding kind of what almost philosophically, what are forces all about, right? So forces have a direction, for sure. So they're vectors. They are vectors. So we are going to be doing more of the same kinds of things, right? Forces will combine in the same way that other vectors did, right? So we're going to eventually, what do you suppose we're going to do if we have lots of forces acting on an object and we want to resolve them down to, and I'm jumping ahead a little bit, but this is kind of the route we're going to go down. We want to resolve them down to one net force that's going to determine what the ultimate movement of the object is. How do you suppose we're going to combine these forces? Vectors, but what's that technique called? Vector resolution. Yeah, we're going to do the same stuff we did before, right? So we'll make a table. We'll combine the x's and the y, and later on we may find that x and y are appropriate directions for some situations. We may end up with some problems where instead of being horizontal and vertical, we do something different, some other orthogonal components that match the situation better. But we'll get there, we'll get there. Okay, so forces have direction. What else do you know about forces? And we'll talk more about different types of forces, as we get into this a little more. That'll be some good food for thought and good discussions. We'll start talking about scales of forces and where in the universe do we see certain types of forces. And there's some very interesting things that we could talk about. We'll go off on some good tangents. But what do you know about forces? Yes, sir?
Does it have anything to do with newtons?
It does. We're going to find out newtons are the standard units for force. Okay. Well, we're not quite there yet. We'll get there after we come up with some quantitative way of describing forces. Yes?
can't think of how to articulate this, but isn't there something like the amount of force or energy between the two interactions?
Okay.
Interaction of two things is the same before and after.
Okay, yeah. So we know that for one thing, and we'll establish this is really Newton's got 3 laws that describe forces very well. And we'll come to talk about that in the future. The third law has to do with, the third law, there's a way that it's described often that we will describe when we get there. But really the best way, in my mind, to describe Newton's third law is that forces always occur in pairs. Forces have to occur as an interaction between 2 different things. A force can't exist, one thing by itself in the universe could not generate a force. Generating a force would be of no value. If there was only one particle in the universe, a force couldn't exist. A force can only exist as a relationship between 2 objects. If there were 2 particles in an otherwise empty universe, then yeah, there could be a force acting between the 2, right? But it has to act between 2 objects. We'll get into more detail with that later. How could you define it? Let's just be really non-scientific for a second. How would you define a force? What does it do? How do you know that a force is acting on something?
Move something?
Okay, it causes something to move, and we'll even get more specific than that. Causes a reaction, causes something to move noticeably, right? Okay. So how could you, I mean, what's kind of like, if you're going to describe this to a 3rd or 4th grader, then how would you say, what does a force do? It is you might have heard this before, a push or a pull, right? That's a good way to describe it. A force is a push or a pull on an object. Okay. So let's take an example here. Now, if I'm going to push an object, let's say I'm going to take this calculator, and I want to slide this calculator along the desk. I'm going to push on it to slide it. Take my finger off, what happens? Stops. Okay, I have to apply a force to push this thing. So does that imply anything? Does that imply that I have to provide a force to this thing to make it move?
There's probably a force between the calculator and the table already that is preventing it from moving just on its own.
Okay, so you got to be careful with this, because this is what Aristotle told us. Aristotle thought he was pretty smart. He probably was, but he got a lot of things just absolutely 180 degrees wrong. It seems to imply that I have to push on this thing to cause it to move, right? If I want it to move at constant velocity, I have to push with a constant force, right? Is there really anything in our observational network here, within our frame of reference on Earth, is there anything that behaves other than that?
Yes.
What?
A ball.
Okay, how so?
It'll keep rolling.
Will it?
Yes.
Forever?
No.
Okay, so even that, it's better than this, but even a ball, if it's a perfectly flat surface, if I roll it, it's eventually going to come to rest, right? So theoretically, based on those observations, I would maybe have to have something like a magnet to push that ball along to keep it going, right? Agreed? There's nothing in our observational frame of reference that's any different than that. Are there things in the universe? Are there places, if we had lots of money, where we could go to take a very expensive field trip to demonstrate that that's not the way the universe really works?
Just
Yeah, just go into interstellar space somewhere, right? If we just took a trip, I don't think this is in the budget. I'll look into it and see. But if we were to go into deep space, and if I were there to take a ball and toss it to you, if you missed it, it's going to keep going. How long before it stops?
Until it hits another force acting.
I mean, potentially never, right? Potentially it might just travel forever, because space is matter's pretty sparsely distributed through space. If we're in deep interstellar space, away from all the other galaxies and things, it's moving pretty slowly, it's likely that it's never going to encounter anything that's going to cause it to deviate from its path. During the predicted age of the universe is likely to end before it ever gets someplace where a force is going to be exerted on it that's going to cause it to deviate from its path, right? So even though you can understand why Aristotle made this mistake, well, he made the mistake of thinking, okay, we got to keep pushing on something. Constant motion is caused by the presence of a force, is what he said. Not true. If we go to outer space, we realize that constant motion is what happens in the absence of a force. Okay, so what is the force here, if I push this thing, that causes it to stop?
Friction between the
Sure, there's some friction, right? And then we're never going to be able to avoid friction except in highly specialized places. And even there, it's almost impossible to completely avoid friction. If we went into a lab and we evacuated the lab, or evacuated a vacuum chamber, let's say, so we sucked out all the gas, and we're still going to have the Earth's magnetic field, though. I mean, Earth's gravitational field pulling on something. Okay, so maybe we are going to suspend something magnetically and push it horizontal. I mean, we could start to approximate a situation where there wouldn't be any forces acting. But to actually get one where there's no external forces acting is pretty much impossible to do perfectly on Earth. We'd have to go far away from any gravitational center to do that, in a place where there is little or no matter. Even in deep interstellar space, though, there's some matter there. It's not much, but there's going to be a tiny bit of friction there. But we might say it's negligible, right? And like many things in physics, what this tells us is that physics is essentially the practice or the unending search for trying to find mathematical models that describe the way the universe really is, right? Think about math. Have you ever seen a line before?
No.
We've talked about this maybe, right? You've never seen a line. You've never seen a point. You've never seen a plane. You never will, because they don't exist. But they're pretty useful in mathematics, right? Have you ever seen a number? No. They don't exist either. But they're pretty useful to us for counting things and ascribing a cardinality to objects, right? So we're used to this kind of thing. We can take stuff that's very abstract, that's non-existent, but forms a really good model for the way the world works. Physics is that way. There is probably no such thing in our universe as a place where there is zero friction, and yet we base the concept of our understanding of forces as, we're going to base them on that idealized model of a place where there is no friction. So we'll call it space, perfect space, where there is no other, there's no other particles to interfere or cause friction, right? But in that case, an object moving along in a straight line will continue moving in a straight line. What happens if you see that ball traveling through space and it starts to turn, or slows down or speeds up? What's happening?
There's a force acting.
There's got to be a force acting on it because its motion changed, right? Right? The normal state would be for the motion to stay the same, and that's what Newton's law of inertia tells us. What's the law of inertia? It's one of those game show questions. If you're ever on a game show, this might be the question that wins you $1 million, right?
Keep moving that direction.
Okay, do you kind of remember the way that, you probably talked about this. Okay, here we go, right here.
An object in motion stays in motion.
Or an object at rest stays at rest unless acted on by an outside force. Okay, good. So that's, in one way or another, you're all fairly familiar with that, right? That's Newton's first law, the law of inertia, right? An object stays in motion unless acted on by an external force, or it stays at rest. Now, are those two different things, by the way? No. Like, velocity of zero is just a velocity, right? Zero is a number, right? So if it's moving if this is the positive direction in outer space, if an object is moving at 10 meters per second in that direction, it's got a velocity of positive 10. It's moving 10 meters per second in that direction.
Are you kidding me?
Wonderful. Okay, let's go to the track. Gosh,
Come on.
just when it's getting fun.
You've got to be kidding me.
Keep trying to go. Is there something I can have the right on?
Sure.
I can take this.
Yeah, take that. That's fine.
Sweet.
Yep.
Thank you.
all clear. You can re-enter the building. All clear. Please come back to the building.
Wait, who won?
That's the next three there.
I don't know. We gotta find out.
No, Molly won.
Big
Molly
bang.
probably. I saw someone.
Oh, good thing I was recording the
Molly
whole
probably.
drill.
Molly.
Okay, so we're talking here. We're talking here about forces. We're talking about the law of inertia. We said that only if an object, if its motion changes, do we begin to suspect that there's a force acting. 10 meters per second in the positive x direction is a velocity. 10 meters per second in the negative direction is a velocity. If an object's moving along at one of those constant velocities, if we see something change, we know there's a force. What if it's just hovering right here? Well, that's okay. That's just a velocity of 0, right? And 0 is just another number, halfway between positive 10 and negative 10. Is 0 that special? Not really, because as we're going to talk about in the future, in physics, here's the other thing that we throw a curveball at you. Everything is relative. So, if you're talking about a velocity of 0, well, that's only, you guys all assumed I meant with respect to the room, right? So we'd say, sure, that's 0. But if we're talking about with respect to a stationary point on the Earth with respect to the center, the surface of the Earth with respect to the center, well, the Earth is spinning around at the equator at about 900 miles an hour. And so, I don't know, maybe we're measuring it with respect to that, in which case this point is moving with a velocity of 900 miles per hour, right? So it all depends. You might, in certain cases, different reference frames are going to make more sense. You might, I don't know if I threw this one at you earlier, but if you ever get a speeding ticket, you might be able to pull out this argument on the police officer. If the posted speed is 65 and he gets you for going 85, well, I mean, really, there's a little bit of ambiguity there, right? 65 with respect to what? Right? It's not clearly stated, it's 65 with respect to the road. You could have mistakenly meant that thought it was 65 with respect to the car in front of you or something, and so it's all relative.
65 with respect to the speed of the earth.
Okay,
Oh, it's
so it's, right, you see what I'm saying, so I mean, I think it's pretty strongly implied what he's talking about, but, I don't know, I mean, it might be.
Doesn't say it on,
fight that one.
doesn't say it on.
Doesn't say it. It
Anywhere.
just says 65.
Nowhere.
Yeah. Okay, so, next question then. So an object moves along, if you see this bottle floating through space
Nice.
at 1 meter per second relative to our stationary ship, okay? If it starts to change its motion, then we know there's a force acting. To different objects, we say that its tendency to keep its motion is called this qualitative tendency, which we call inertia, right? Do some objects have more inertia than others? Lily shaking her head, yes. Give me an example. Give me an example of two different objects that have different inertias.
Like ladybug on there, and then it hits a window. The window's probably not going to break with not as much force as the penetrate.
Say it again, if it's a,
If a ladybug.
okay, ladybug compared to a baseball or something.
Yeah.
Okay, so what's ladybug has less inertia, right? Okay. What if we were to compare a soccer ball to a bowling ball?
Yes.
Which one has more inertia?
Bowling ball.
Bowling ball, prove it.
As long as it's going.
It's hard to change
As long
its
as
direction
it's
as
moving.
moving. It takes more force to move.
Okay, it's harder to change its motion, isn't it, right? And we could prove that. Now, is that, okay, now we're gonna talk more about this in the future, but is that a result of, what would we equate that to? Its weight? Oh, okay, now we're getting into, we're jumping into some
To its
equations.
initial
We're not quite ready for those. Yeah, we're getting there. But is inertia related more closely or directly to an object's weight or its mass? Or is it a tie?
Weight.
Weight? Okay. Okay, well, if we're gonna talk about weight, I guess we better at least do an informal definition of weight. What is weight? Force of gravity on an object, yeah. The most effective weight loss plan that I know of is to just take a rocket to the moon. In a relatively short period of time, you can lose a lot of weight, right? So it's a little expensive, but it does work. It's really effective. Okay, so weight is the force of gravity acting on an object. What's mass?
Amount of matter.
Stuff.
Amount of matter in an object. Okay. So then let's do a little mental experiment here. So we're going to determine which of these two quantities has the biggest impact on inertia, is most directly related to inertia, weight or mass. Okay. So let's take our soccer ball. We're going to paint it black, and we're going to take a bowling ball, which is also black, and we're going to go into deep interstellar space. What is their weight there? Zero. Okay. So if you were going to we're out in outer space, if you were going to take a boost from your retro rockets and go firing up to these things, and you're going to kick one really hard, which one are you probably going to choose to kick?
Soccer
Well,
The soccer ball. Why? The weight's zero on both of them. What difference does it make?
It's less massive.
Okay, so you guys want to change your answer then? Right, the weight could not have anything to do with it, because in a place where they have the same weight, there's clearly an object that is going to be more resistant to changes in motion, right? That's going to be the bowling ball. You don't want to kick that. Well, I mean, you're going to break your foot, right? Regardless of whether it's on the ground or in deep interstellar space, where its weight is zero, it still resists changes in motion much more strongly than that soccer ball does, right? So it's got to be mass that's related to inertia. Weight is accidentally related to inertia on the surface of the Earth because we equate the two things. I mean, if you go into a gym and you tell somebody to put on a 45-pounder on the bar, well, we all know what you mean. You're going to put a plate with a weight of 45 pounds on the surface of the Earth onto the bar, right? If our planet were much more, the topography topographical differences were highly exaggerated. So our peaks were thousands of miles high instead of just miles high. Then, and somehow people were able to live in all these different locations. We might want to change the way that we lift weights in a gym, right? In that case, putting a 45-pounder on wouldn't make a lot of sense, right? Because 45 pounds is going to be, the same plate is not going to have a weight of 45 pounds up on one of these many thousand feet high mountains compared to down in one of these really deep trenches. Agreed? How come? Okay, because the gravity is going to affect it differently, and we'll explore that in more detail later. But we can all kind of agree that, right? We know that if you go very far away from Earth, gravity diminishes, and so therefore, if we go up even a really high, many thousand-mile high peak, it would also diminish a little bit, right? And so, once again, I mean, we're seeing that there is a distinct difference here between weight and mass. They're not the same thing. So what is mass then? You told me it's, I mean, what is it? It's the quantitative equivalent of inertia, isn't it? Inertia is just this concept, this almost philosophical idea that an object with inertia is going to be resistant to changes in motion, right? Mass is how we can attach a number to that. What's our standard unit for mass? Well, yeah, I mean, but kilograms would be the MKS standard, right? Would be the SI unit standard. Grams are just related to that, obviously. But the kilogram measures what? Well, how do we quantify a kilogram? If we wanted to come up with a standard for a kilogram, how could we do that? Okay, you're right. It does have something to do with a standard measure. But how could we come up? I mean, how are you going to approach that? If that was someone said you got to come up with a standard measure for 1 kilogram, what could you do?
Choose an element, take a set number of atoms of it, and say, okay, the number of atoms for this specific element is 1 kilogram.
Okay, that's one way to do it. So you're gonna break it down to a certain discrete number of completely uniform objects, all of what have some measurable mass maybe. Okay, that's one way to do it. That's difficult. It's real difficult to do. Is there a way that we could maybe be not as accurate, but do something like even in this room, that we could try to go about coming up with a standard for mass?
Could you take any object?
It could be any object, sure.
Just say this
This is a
and then go
block,
up basic
sure,
things.
based on those, okay. But then how are you gonna measure increments of blah, of our new unit for mass? I mean, what is mass? Now think back to what it does, right? Mass is the quantitative version of inertia, right? What does inertia mean again?
Object's resistance to a change in motion.
Ah, okay, resistance to a change in motion. So then how could we quantify how much mass is there? By measuring what? Resistance to a change in motion. By measuring how resistant an object is to change in motion. So what might that be? I mean, what's one fairly uniform way that we could measure an object's resistance to change in motion? What do you think? It's a harder problem than it sounds like, isn't it? I mean, we kind of take this stuff for granted, but there's got to be, I mean, how would we do that? What do you think? We might take a stab at some of this stuff in class over the next few days. We could set up some equipment and see if we can come up with a way of maybe, a way of maybe trying to come up with a standard for mass, something along those lines. Yeah.
Couldn't you just drop something?
Let's do it. Let's drop something and see how long it takes to get to the ground.
But if you have some
Okay, I'm going to drop things of fairly different. What do I need? I need something.
it'll take more time.
That has to do with air resistance.
You know what? I think that might be easier.
Okay.
Mr. Cooper said you can borrow his bar and Cooper.
Here we go. Ready? Which one? About the same.
It's Luke that's
Okay. Pretty different masses.
Again.
Again.
Higher up.
Throw it. No, you don't have, I'm kidding.
One.
Wait, the
Yeah,
floor.
he's cheating.
Cheater.
There.
No, no.
Right there.
Right there?
The bottom of each one has to be at the same level.
Higher,
Yep. Oh, that's too much.
lower,
Right there?
That's better.
lower. Right there.
I mean, there's gonna be, I'm not highly trained in doing that, but it's, would you agree that it's close enough to a tie?
Yes.
Well, what's going on? That one's got more mass. How did that work? Explain this. You guys can't explain this stuff to me. What's going on?
Force of gravity applies equally to how hard it hits the ground.
How hard it hits the ground, maybe. Okay, well, there's,
So Seth's gonna put his foot there, and whichever one
Hurts
more, that has more mass.
okay, so that's, okay, that would be a place to start. The place to start would be to say, okay, if we're gonna drop objects from equal heights, they're both subject to the same acceleration, right? So ignoring, I mean, it's not gonna work for all objects though. We gotta be a little bit particular about this, because I could drop these two and it's not very close.
Resistance.
Okay, but that's different, because this one is, would you say that it's not the fact that it's got less mass, it's the fact that it's got a lot more air resistance acting on it, right?
Drop this.
Yeah, if you crumple it up, exactly, if I crumple it up, now it's about the same, right? Same piece of paper, right?
This is yours, actually.
Oh, it is, okay,
Yeah.
all right. So if we drop objects that are fairly aerodynamic, and we're throwing around all these physics words that we don't really totally understand yet, but we get an idea, right? Then one thing we could do is we could say, okay, we could measure how resistant they are to change, because they're going to hit the ground we drop them from a uniform height. We're going to call it I don't know, it's one flotilla. That's how high it's going to be. We just made up a word. And we have a standard device that's going to determine how high we drop them from. And then Seth is going to go through a process of, he's going to very accurately try to correlate the amount of pain in his toe to the amount of force required to stop something, and how loud he says ouch could be one way of quantifying the amount of mass in
I
an
don't
object.
say ouch either.
Isn't there a way to measure pain, actually?
Probably.
Kind
yeah.
of.
I know, I've heard like a really cool term, and you can like plug someone into like a machine and.
Yeah, there probably is.
Plug
It's
someone in.
probably
Someone
is.
into a machine.
Probably is how much like of an impulse is like that travels through.
Yeah, my bet is that it's probably not linear. It'd be pretty hard to do, but at least there's the first credible suggestion I've heard that actually does attempt to quantify. Okay, I mean, there may be some other things though too. Maybe we can do something like we could apply a standard force to an object that's resting on one of our motion carts. If the cart is flat and we're going to use a really standard rubber band, we could stretch the rubber band and let it go, stretch it a finite distance,
See how long it takes.
and see how long it takes, right? To see how much the force that's stored in that, the force that's being applied by the rubber band, how much of an effect does that have on the object as measured by the amount of time it takes to travel through a certain distance, maybe. Okay, so, I mean, there's some things we could maybe do, right? Okay, so mass is what we associate with inertia. So what has more mass? A bucket full of lead or the same size bucket full of styrofoam? Lead. What has more mass? A kilogram or 10 kilograms of talc or 10 kilograms of lead?
It's the same.
What's that, the lead? 10 kilograms of lead has more mass than 10 kilograms of talc.
It's the same.
It's just a really lightweight rock.
There'd be more.
It's the same mass.
Lead.
It's
Lead.
still because there's less
They have the same mass.
That's density.
Yeah, it's there. Okay, so we could use, let's make it even more dramatic. Let's take 10 kilograms of styrofoam and 10 kilograms of lead. 10 kilograms of lead is not very big. 10 kilograms of lead is not a very big piece of lead. 10 kilograms of styrofoam, it's a big block of styrofoam. But their inertia is equal because you told me, kilograms is the quantitative measure of inertia. That's our standard unit for mass, right? So what's the same about them? They don't look the same at all.
How much matter there is?
How much matter there is? It's just distributed differently. If we were to take out our physics angle grinder, that's going to grind things down. This is a really Acme store angle grinder. It grinds things down not just to rubble, but it's actually going to go further than that. It's going to grind particles down to their constituent subatomic particles. if I ground down the 10 kilograms of lead and the 10 kilograms of styrofoam into their constituent subatomic particles, I want to have the same piles. They're just put together in real different ways, right? You get the idea? Okay, so mass is literally the measure of the amount of matter in an object, right? Not its distribution. Density is different. Lead is much more dense than styrofoam is, right? But the total mass, 10 kilograms, is 10 kilograms, right? Okay, so we're getting there. We're kind of building up our understanding here of how we deal with forces. So next step is, what are we going to do if we have a bunch of forces acting on an object and we want to find a way to simplify the situation, to resolve the forces, is what we'd say in physics. So I'm going to pull up, this is just from the OpenStax text. But what we've got going here is, seen from above, we've got two ice skaters pushing on, in the pink outfits, pushing on the person in the blue outfit on ice. They're on ice. If each of them applies a force, what's the tendency of the force F1 going to be? To what kind of a change in motion is that going to cause to the stationary skater? It's going to make her move in which direction? To the right. Okay. What about F2? Straight up, right? And assuming this is laid out, we're looking down, in the Y direction or to the north or something. So what do you think the resultant is going to be of all that? Okay, so it's going to move, there's going to be a combination of both of those. Okay, now what if each of those forces has a magnitude of, let's just say, 100 newtons. And Newton is going to be our standard, we'll get to that later, but that's our standard unit of force. Okay, if each of those forces, each person is pushing with a force of 100 newtons, what's going to be the magnitude of the resultant? Is it going to be 200 newtons in this case?
Would be the square root of 200 newtons.
Yeah, in other words, vectors have direction. Forces are vectors, so they have direction and magnitude, right? The direction is obvious, indicated by the arrow. The magnitude is indicated by the lengths of the arrows. So if I've got this vector acting in the x direction and this vector acting in the y direction, when we add those tip to tail, we get the resultant vector. But because neither of these vectors are not collinear, they're not pointing in the same directions, right? They're not just going to add normally. We've already got some familiarity with this. They're going to add by vector resolution, right? So it's going to be less than 200, right? What would be the resultant if I had one person pushing with 100 newtons this way and another person pushing 100 newtons that way? Okay, add 0, right? Okay, all right.